Next up is Andrew Betts, who will talk about design factors for decentralized edge applications. The stage is yours, Andrew.
Thanks, Marcus. So, hi, my name's Andrew Betts. I run developer relations for Fastly, and I've been building web applications for a very long time. And it feels like almost every year someone comes up with some new school of thought on how we should build distributed applications. As I was reminded quite recently, there are some pretty bad ways of building distributed applications. For example, the UK government should probably choose a better tool than Microsoft Excel to manage a database of millions and millions of COVID-19 test results. So this is not a very good way to build a distributed application. And today I want to spend 20 minutes or so talking about a better one. Let's start by thinking about the traditional full stack of components that make up a distributed system, or any kind of system, actually. Traditionally, you have to manage hardware, operating system, server, processes, and the actual application code. And pretty quickly, we realized that the constraints of hardware were not at all useful at the code layer. So we added virtualization. And now you have a container engine or a hypervisor, a bunch of operating systems, and all of this requires patching. And so you actually spend very little time on your actual code. Now, no one wants to run their own data centers, so we pretty enthusiastically adopted a so-called infrastructure as a service, which abstracts away this bottom layer. But then in 2011, Heroku came along and they created a new layer of abstraction that became known as platform as a service. And it turns out a lot of people don't want to run their own container engines or their own operating systems either. But accepting this higher level of abstraction came with added constraints, limitations, and design decisions that you had to apply to your application architecture. And Heroku's founder published some details of this in what they called their 12-factor application design. And this actually has set the parameters and still is pretty accurately descriptive of many of the web applications that we build today. So of those 12 seminal design principles, several stand out to me as empowering the move to serverless rather than just being good software engineering ideas in general. And these are things like using stateless processes, which expect to run concurrently, which are resilient to being terminated randomly. And also the treatment of all connected services as equivalent to third-party integrations. Then in 2014, Amazon releases Lambda, and now we have functions as a service. We move up another layer of abstraction, and we don't have to worry about processes and runtimes anymore. You can just focus on application code, and we only pay for infrastructure when we're actually processing traffic. So this serverless world brought us a bunch of new constraints on things like per request processes, maximum runtime, and memory usage per request. And we had to learn new abstractions for things like state management, but we gained the benefit of seamless and almost limitless scalability. On a personal note, coming from a PHP background, I've always been quite familiar with the idea of per request processes. And then I moved into Node.js, where you're looking at a process that's handling multiple requests. And so this feels like to some extent a new take even on an old idea. Anyway, it seems clear that the design factors that we learned to love from Heroku prepared us pretty well for migrating to serverless. And with this new serverless philosophy, we've achieved huge advances in agility and scale. We've got no idling costs. No idling costs. We've got looser coupling between components. The only thing we have to manage is the application code, and it's much quicker and easier to iterate and build new things. But consider this, none of these benefits directly impact the end user experience. These are all improvements to our developer experience and productivity. We still mostly run our application logic in central locations. And at most, we have some kind of network of caches on a conventional, fairly dumb CDN that replicates fully formed content in locations closer to our end users. So in this case, you can see, what I'm visualizing here is the idea that we have one central location, perhaps in New York, and we have a network of caches across the world, which are doing nothing intelligent beyond just remembering content that passes through them. Or at best, maybe you deploy infrastructure all over the world. But then you have all of this additional infrastructure to manage. It's all very visible to you. It's very intentional, and you have to spread and balance that load by yourself. It's an additional overhead in a world where we're trying to remove that overhead from the way we build applications. Let's revisit the stack of stuff that we started with, most of which we've now abstracted away in a serverless world. That abstraction means that running code in more than one place is something that's no longer an impractical idea. So we can conceive of a kind of a pipeline, a chain of processing nodes that we can string out between the core of our infrastructure and the end user, each made up of a full stack of components, but crucially components that you don't have to provision and you don't have to manage. Now we can decide where in this pipeline it makes sense to run our logic. As we move along this pipe, we find a larger number of parallel instances, and different benefits and constraints emerge. So for example, the core infrastructure, which might be, for example, AWS or Google Cloud Platform, this will be the cheapest place to store large data sets, whilst the client device, which could be a web browser or a native app running on a phone, for example, is the best place to do processing because it's free. But of course, on the client, you only have access to one user's view of the system. At the edge, we might have access to state, but maybe it's a cache or a replica, or maybe it's a distributed data store that's designed to propagate updates asynchronously. It might not be complete. With service workers, we now have a second way to run logic on the client, and using WebAssembly, we can further extend and harness the capabilities of client devices. And between the client device and edge networks like Fastly that have maybe a few hundred points of presence, there's also the possibility of 5G introducing processing capabilities into cell towers, which means your app running on potentially tens of thousands of points of presence that you don't control or provision, or in fact have anything to do with. But that shouldn't scare you. After all, we're used to running code on devices that we don't control. The client, the device that the user is using to interact with our app. And there are millions of those, or even billions if you're one of those lucky apps that we all know and love. So in summary, where we ideally put logic in this pipe is a function of things like the number of users that are affected or will benefit from the operation, whether we need access to state and what kind of state, and whether that state is global or local, and whether it needs to be up to date or complete. And in fact, state will be a recurring theme as we look at this. What kind of CPU or memory resources we need to complete the task, and any regulatory, privacy, or security considerations that we want to factor in as well. In terms of benefits to the end user, the further we move our processing down the pipe, the lower the latency for the user. So here's a simple example app, running on Fastly's edge that takes an input, interprets it as Markdown, converts it to HTML, and returns the rendered result. And this is using our computer edge platform. So from my home broadband connection in London, the average round trip time to complete one update is under 10 milliseconds, which allows us to performantly execute a round trip to the edge on every keystroke. And importantly, this kind of low latency can be expected pretty much regardless of where I am in the world, because edge networks like Fastly are designed specifically to provide points of presence near all major population centers. A toy example like this is great for demonstrating the potential for offloading work to the edge, but actually let's consider some of these pipeline trade-offs and think about if I'm running this Markdown app in the right place. So this is a very simple process using small self-contained logic, which is not proprietary, and the input and output are both on the client side. So this logic should really probably be a client-side process. But let's imagine that instead of generating HTML from Markdown, my function is generating it from data that it's loading from a CMS. So that CMS, or content management system, that sits in my core infrastructure and acts as a global data store. The edge, meanwhile, can hold a cache of any API responses received from the CMS, which allows potentially many different pages to be built using the same set of core data in different combinations. For example, imagine two users request the same article from a publication. They might receive pages that both contain the same data from the same API call, but with differences based on those users' preferences, permissions, or identity, all of which we can compute and customize using edge attached data or state imported from the request itself using a cookie. So, simple example, one of those users might have access to that article and the other one might not, and might receive a teaser of the article alongside a paywall. Imagine your React app doing server-side rendering for each user individually, or your e-commerce site pulling product inventory data and composing it into pages at the edge. None of this actually requires any major departure from the way that we already think about web application architecture today. But here are some other ideas for use cases where we can shift tasks further along the pipeline and benefit from edge processing. So anything involving personalization, localization, authentication, or authorization, these are really low-hanging fruit when it comes to moving compute to the edge. I like to think of these as the outer layers of the onion if you design your application in a kind of layered way. And so these kind of layers often are the first stages of request processing that you do, and so they can often be quite easily moved to an edge computing platform. Other more interesting, or potentially interesting use cases are things like beacon termination. A lot of Fastly customers doing this, where you receive a log message at the edge, and then you aggregate those log messages and emit and re-emit them in a more efficient way to, let's say, a bucket store like Amazon S3 or Google Cloud Storage. Anything that you might describe as a facade, for example, a transformation layer or a migration layer to provide compatibility between old and new versions of applications. These are great things to move to the edge as well. A good example here might be, for example, let's say you have a REST API, an API designed around REST principles, and you want to expose a GraphQL API. You could run GraphQL at the edge and convert GraphQL queries coming in into REST queries that you then make to your legacy API. So far so good, but to go further, we need to some extent let go of the idea of perfect being the standard that we want to achieve. We already have, in many ways, by embracing edge caching and conventional dumb CDN setups, where CDNs will just cache copies of pages. But I think it's worth properly wrapping your head around this as a design goal rather than an unfortunate side effect. So in 2007, Pat Helland, who was at Microsoft at the time, wrote this really cool blog post that I love, in which he asserts that what computing is basically just memories, guesses, and apologies. It's a brilliant and very short piece of writing. Unfortunately, it seems to have disappeared from the internet, but you can find it in archive.org, and I'd recommend you go look at it. And if we do this, if we kind of let go of this single consistent view of the world, that unlocks quite a lot of interesting possibilities for the way that we can redesign our applications to make them faster and, to some extent, also more reliable. So, for example, we could accept writes at the edge. Now, almost all applications that use content delivery networks today do not do this. They use the content delivery network to remember content that's passing through it, and then they will only answer requests from the CDN if the CDN already has a fully formed copy of that content. And requests that are write requests, like posts to execute a login or something like that, will just pass straight through the CDN without being touched at all. But imagine that all writes can be accepted locally by whichever edge server handles the request, written to a local representation of state, and then synchronized as needed with the core infrastructure or other edge servers in other locations. This is particularly interesting for use cases where the writes are updating data, which you need to be up to date within the same geographic area where the writes are happening. So for example, dating apps like Tinder or ride-sharing apps like Uber, these are good examples of use cases where we can shard this information across the world, but still enjoy access to some kind of view of the global state, even if it might be slightly out of date. So let's say I swipe right on someone who's on the other side of the world from me, there's a chance we might not match, even if they at the same time swipe right on me. But with good enough data reconciliation, we can mop up these kind of edge cases later, and we can still give everyone a great super fast user experience. Using the same principle, we could imagine that COVID track and trace apps could submit check-in data to their local edge server and receive a really rapid response, while the edge then aggregates and contributes the resulting aggregated data to some kind of central service. Now, with relatively crushing inevitability, I'm obviously going to go all universe brain on you at this point and suggest that maybe we get rid of the core infrastructure entirely. Are there any large-scale applications that can exist with no centrally coordinated state at all? Well, yes, why not? And there are actually some pretty good reasons for thinking about designing an application like this. So, for example, applications whose primary purpose is to provide a means of storing and organizing personal data, like Gmail, Pinterest, Dropbox, these kind of apps benefit from locating the primary data store for each user close to where that user is physically located. And with edge cloud platforms, maybe we don't need to spin up separate storage instances in multiple cloud locations. Instead, just allow the edge platform to move the data to where it's needed. A friend of mine who works for a newspaper that's a Fastly customer suggested to me that we could move their primary data store to different parts of the world based on the time of day, because their journalists are active and working and writing to that data store from different places in the world based on what time of day it is. So whilst migrating a database from one primary data center to another sounds like a really big and difficult thing to do, and something you wouldn't do unless you were going to get a massive benefit from it, if it was almost free and you didn't have to do anything to make it happen, then why not? If it's a small improvement, it may still be worth doing. And there's really no reason why we can't do that. Another use case which is interesting is regulation. And regulation is now a huge consideration that we have to apply to decisions about the global architecture of our applications. Where a country or territory legislates to require data to be stored in country, edge networks provide a way to make that a practical option for even relatively small websites. Here, for example, you can see a kind of illustration of how users might be directed to an edge location that's actually not necessarily their closest one, but it's the closest one that exists within the same regulatory environment that they're in. Another interesting case that I like to think about is, this one, is rate limiting. Say you want a user to be able to make a certain number of requests per hour, but that's globally, right? Because good users will most likely make all their requests to one edge server because they're not moving, or they're not moving very fast. But attackers are likely to send their requests evenly to all the edge servers in your network to maximize their usage of the allowance, and they'll bet that there are going to be delays synchronizing data across the world, or that maybe you're not sharing that state across the world at all. So what if, for example, you started counting requests at each individual edge location, but then once you break some lower threshold, you would then pin that count for that user to that location. So if the user then sent any requests to any other edge location, they would be proxied through to the location where they are being counted. Good users, who are acting normally, receive no additional latency. Attackers are subject to a single global rate limit. Centralized for one user, but across all users, the data storage is still distributed. So this is a glimpse into one scenario in which an edge location might want to directly communicate with another as part of a specific request or transaction. You could also conceive of that being useful for, say, relaying chat messages between users who happen to be connected to different edge locations, or streaming game updates for users connected to a multiplayer game session. One of my colleagues recently implemented Doom on our edge compute network, and managed to make a multiplayer version by picking an edge location which was equidistant between the two users. So let's say I connect from London and one of my colleagues connects from San Francisco. We'll both initially get connected to our local edge, but those edge servers can then negotiate and redirect us so that we both end up connected to, say, Chicago or New York. This is all pretty exciting stuff, and it gives us an idea of how future applications will benefit from edge computing. How can we boil this down into a set of design ideas or principles similar to Heroku's original 12 factors? Well, let's start by going back to those 12 factors and highlight from those original 12, the 5 that I thought were particularly important in serverless. And I'm going to add to those 2 more that I think are becoming increasingly important as we consider the architecture of our serverless applications. The first one is remote state. An edge application assumes that its persistent state is controlled remotely but cached locally. It updates local representations of that state and makes use of mechanisms in the platform that reconcile updates to that state asynchronously. And to me, it's that mechanisms in the platform thing which is critical. It's the fact that you don't necessarily have to figure out how to do this yourself. Platforms will provide these kind of mechanisms for managing state and will increasingly provide more and more options around whether you want that state to be local, how fast you want it to be synchronized, how many times you want to update it per hour, whether you need to be able to update it from the edge or whether you just want to be able to update it from an API and so on. And the cost and the performance characteristics of those state systems will depend on those choices that you make. The other one is no single view. An edge application does not need to have a complete and up-to-date understanding of the world in order to operate correctly. And the sooner in your architectural evolution that you kind of discard this attachment to the idea of having a complete and comprehensive view of all global state, the sooner you're able to scale more efficiently and more dramatically. So I'm going to add those in and say, you know, that this is still very much a work in progress in terms of trying to map out the future architectural design principles that we will apply to serverless. And I would love to get your feedback on whether I've chosen the right ones, whether there are other principles that need to be applied in this new world as well. That is all I have. Thank you very much. And if we have time for questions, I'm very happy to take them.
Hani asks, is there a white paper for such implementation?
There is a blog post that I wrote in December that is essentially everything I just said in text form. So I think that's probably the closest I could get to offering you a white paper on it. Whilst you're looking at, what I would love to do, if I've got a minute, is to show you a demo that we just released yesterday, which I think is really cool. So one of my colleagues has been busy with the source code for the classic arcade game Doom. And I absolutely love this as a demo. So what we're doing here is kind of crazy. It's sending a request to the edge server for every individual frame of the game, which is a really silly way of trying to run a game. But it just demonstrates how quickly you can turn around a request from the client to the edge versus having to go back to central infrastructure. And it also shows, the flexibility of edge compute platforms. You can do pretty much anything you can dream up. Thanks very much.